my name is Sarah Freeland, and for my project, I studied the detection of image tampering using watermarking and steganography. Photoshop can be a positive resource. You can modify images using filters, removing acne, adding in a friend who didn't make it for the picture, for the event, lots of different positive things. But there's also malicious things that Photoshop can be used for. It can be used for catfishing on social media profiles. It can be used for slandering in news sources. It can be used for false advertising on marketing, different things online like Amazon. You might see an image of an object which does not match what you receive. So the question is, can I trust the image I'm receiving? The different studies done that I researched showed different ways to deter modification of images, whether it be through a watermark symbol or through some form of encryption that makes the image unreadable without the key. So with these different methods, we found that the watermarking with a 2D WT DCT, second level discrete wavelet transform, and discrete cosine transform can take an image and transfer it over to the frequency domain. And then inside of that domain, you can hide a sequence of numbers, or you can hide another image. In this case, they use a sequence of binary numbers to mark the image as some type of watermark. And then it is converted back over to the normal time domain. And that image can be sent. And when you want to see if the image is being copyrighted or whatever it may be, you can perform the decoding process and see if that watermark exists on the image. They chose to go with the second level discrete wavelet transform because it had a lower ability to be detected in the frequency domain. So if you look at the images in the graph on the left, the top row are a single wavelet transform and the bottom row are the discrete or second level discrete wavelet transform. So in this method, you can see that there is a larger change between the right and the left photo on the top than there is on the bottom, meaning that it's more distinguishable that something has changed when you inspect the frequency domain for a single wavelet transform. Then they also perform different attacks on the image to see how it would hold up with the watermark coming out, and the different versatility of how it can withstand different noises, different filtering, different things that may happen to an image to try to erase said watermark. The other type of encryption that I studied method was the AES, Advanced Encryption Standard, and the RSA, Rivers, Shamir, and Altman, Least Significant Bit Encryption. This is a form of steganography where you would take the image and you would first use the encryption standard, the AES encryption standard, to convert it over to a salt and pepper image that looks like garbage, as you can see from image B and C. And then you would take the key that is used to put it in that encryption format, and you would encrypt that key with RSA. And then instead of having to hand the user on the other side both the encrypted image and the encrypted key, you could take the encrypted key and hide it inside of the actual image using least significant bit encryption. So in this process, you just simply hide it somewhere in the image and have some process to find it and pull it back out. That is the steganographic part of this encryption process. So the different approaches that I wanted to test to see if we could detect the images are kind of based off of these two methods. Those were ways to deter someone from modifying the image, whether it be a watermark that is lasting throughout so you can claim that image as some type of copyright, or the least significant bit encryption alongside the other encryption that's used to make the image indetectable for the sake of privacy. So the processes I used were invisible watermarking in the bandpass filter to overlay a watermark on top of the original image and use that on receiving it to see if it has changed, as well as least significant bit encoding, where you can do a bitwise comparison on the receiving end to see if things have changed. So for the watermarking method, I originally derived this from the Albert Einstein Marilyn Monroe illusion. In this illusion, if you're standing close, you can see Albert Einstein. If you're further away, you can see Marilyn Monroe. This process uses high and low frequency patterns of how the image appears and how your brain detects them to see two different images in one image. So the thought process for what I was trying to derive is I would like an image that can be hidden inside of another image where you still see the one, but the other one still exists in a frequency band. Now, I didn't want the watermark to be visible, so I used a very narrow band instead of two wide bands. So to decode this process, I first attempted very similar to the two images just being filtered, one at high and one at low, and overlaying them. However, I found that if you simply filter the watermark in that same small band, then very little of the watermark is left to be used for the decoding process. So instead, I took it and I passed it through a much smaller fast Fourier transform so that it was a smaller image being output, and that could be reshaped into the bandpass filter. And then that would be combined with the original image that had passed through the band stop filter. Those two would both be converted back into the regular domain and output as the image, which could be sent over email, wherever. And then on the receiving side of that email, you could pass that image back through the decoding chain and get two different outputs. So the first one would be the image once the watermark has been removed, and the second would be the watermark itself after it has been reshaped to the smaller image once it is taken out of that bandpass. So the two images I chose to use were the first being the main input image that we used throughout the class, just the self-portrait we took at the beginning of the semester. And the second image is the watermark that I created in Paint. It was rather simple. Then when I encoded and then decoded to see what the original image would look like, just going straight through without any photoshopping occurring, I found that there is a lot of difference in the output watermark, meaning that the fast Fourier transform has a large effect on how it ripples into the other image as it's interacting. Because this is not a point-to-point, it's a fluid transform, I realized that this is going to have a lot of issues for being used in a detection process. However, when the Photoshop method being used is a open and closed morphology, which is supposed to be similar to a filtering that may be used in some type of Snapchat filter to remove blemishes on the skin, to just smooth out the image, that there's a large impact on the Photoshop watermark. As you can see, the watermark wording is almost removed entirely, and this candy cane striping at the top and the bottom of the image has been introduced. However, for smaller portions of the image being modified, like just the top left corner, there's almost no effect whatsoever on the Photoshopped watermark. As well as when I removed the entire top half of the image, the top 500 bits, there was very little effect on the Photoshop watermark. So this is very effective if you want to add some type of copyright label to your image to pass through, to claim this is ours, we did this. It's going to be very resilient against different attacks, but it's not very useful in detecting whether or not an attack happened. So the other process that I studied was the Steganography least significant bit encoding. I used two different encoding elements, the first one being an input text by the user and the second option being a checksum. The checksum goes through the second to least significant bit and third to least significant bit and sums both of those numbers and then uses the bitwise XOR operation to combine those. Many other checksums could be used. This is just the one I selected for this project. And then I used several different methods to find the best way of hiding that data within the image. I repeated the same pattern across all the bits. I tried repeating it on every xth bit. I tried padding a random array around that data. I used a preamble function, with the preamble being a wavelet form of highs and lows and then speeding up and then repeating the same cycle. And although that could be modified to something else. And then I used the preamble combined with the padding function. Now, I found that the best method, personally, from what I saw, was the repeating over every X bit, because this still leaves most of the information of the image, whereas the repeating across all bits and the padding random are both going to introduce a lot of change across the image, just in the least significant bit. The rest of the image stays the same. But ideally, we'd like to maintain the most of the original data as possible. So by repeating across every X bit or simply using the preamble are the two simplest ways to hide the data inside, but still leave the majority of the information the same. By using the repeating across all bits, it's very successful in detecting the changes, but it introduces a cyclical pattern that could be detected most easily of the different methods when doing some type of a least significant bit detection process. So if you're trying to hide this against other people being able to detect it, I highly do not recommend using that method. The original image versus the encoded image, just using one of the different types, I believe this is one of the repeating patterns. It has almost no effect on the image, so because it's just the least significant bit, the human eye can't detect that small of a change. So if you look at the two images, they look the exact same. So I created a table of the different passing and failing of these different types and methods. And as you can see from this table, the most successful, you want it to fail if it has a modification. So the most successful amount of failing happened on the checksum method for the repeat across all bits and repeat across every X the bit, the combination of those two. If you use the input text, then it mostly succeeded, would be mostly successful across the every X bit and across the entire image repeating, because that hides the data across the whole thing. So you're checking every single bit for changes. Now, the X bit is going to only be every X bit, of course. Now, if you use the preamble, that could hide it with the method we set up, it could hide it randomly inside the image. So if you only change the top little corner, then if the preamble is hidden in the bottom right, it's not going to detect that change in the top left corner. But the checksum function being added in with the preamble is going to allow for that change to still be detected, because the checksum will then fail. So by combining the checksum method with the different bit hiding operations, it was very successful. So my recommendation is to use the repeating across every X bit to reduce the amount of data that's changed along with the checksum, because it is very successful. Now, going back to the actual code itself, I used two main files. First, I had the filter file, which is the watermarking method, and then I had the least significant bit file, which is the other method. So for the main file, for the filtering, you can set the different input values. I set a threshold so that the circle where the data would be applied is at 500 in the frequency domain. I decided to have my images be squares because it would have been a lot more processing to change the filters to work for rectangles. It is possible. I just did not choose to use that for the scope of this project. And then I used a ratio divide number. I have it set right here as 1. And if you run it with a small number, then it's going to hold the same weight for the watermark as for the main image. And this causes the watermark to provide aliasing on the image itself. So I found that if I reduced it to a smaller amount by dividing, with that ratio divide being by 20, then the image will have almost no detectable changes between the original image and the encoded image. As you can see, it does not look any different. Then in this, you can go down to the bottom and select different Photoshop methods. So I have a open close method, as I talked about. I've got the hiding. If you have just this one, it enables the image to just come do a pass through. So it should be the same encoded, decoded, no changes. So that one should look like there's nothing different. This one will allow for the top 500 bits to be equal to 0. And then this one will do just that top little corner change. So each of these different methods can be run and tested to see the different outputs, and all of those graphs are labeled according to which image is being shown. So the original, the Photoshop, and the decoded, the original encoded and decoded. So you can look at those different comparisons. Over on the watermark, you can see what the output watermark should be versus the Photoshop one. Obviously, because it's not the same as the input, if the user only has the input, they're not going to have the output watermark. So when you look at this, it's always going to look like it's wrong. So this method is not going to be useful in detecting changes. Then I ran my main least significant bit, where you can change which method is being used up here. You can set the checksum to be true or false. If it's false, then it'll use the input text. And down here, you can change those different techniques that are being used. So we're going to go ahead and do using the checksum, setting the bottom or the top 500 bits to be equal to 0. And the output will be just your encoded and original image, as well as a message saying whether or not it passes or fails. So obviously it failed because it's using that checksum, and we showed that that was very effective. So this is my project. And in conclusion, I found that using the least significant bit method is the most efficient in being able to detect the image modification, specifically using the checksum paired with the X bit rate. Thank you.